Yeah. Today I'll be presenting my work on autonomous database as a service for tuning relational databases. This work was carried out for tuning database instances of a cloud platform where we have several hundreds of thousands of database instances. We already have existing set of database tuners, but they are not ready for tuning production database instances. In this work, we try to showcase the challenges that existing database tuners have and the solutions for them. In a nutshell, the outline that I would be covering today as part of the talk is as follows. So without wasting time, let's get started with the challenges that existing tuners bring to us for production systems. So the first challenge is scalability. Uh, so existing Bayesian optimization style tuners like AutoTune are less scalable. So this is because a fully trained AutoTune nearly takes 200 seconds to generate a new recommendation. And on the other side, the databases periodically ask for recommendations at every 5 to 10 minutes. So our objective here should be that the tuner instances should be able to generate recommendations for hundreds of databases and not just a couple of them. The second challenge is high quality samples. So this is the case like on production systems, the load is often low and we do not know if the database actually needs a tuning. In such scenarios, when the metrics are captured, they are classified as low quality samples. This is because the metrics were captured when the database didn't require any tuning, or say when the load is nearly zero. In case of reinforcement learning based tuners, this causes a longer training time, whereas in a Bayesian optimization style tuner, this has an adverse effect. This is due to the fact that Bayesian optimization style tuners leverage past tuning experiences. So it might happen that a Bayesian optimization style tuner like AutoTune will leverage this low quality sample or low quality metrics captured to tune another database instance. So this has a cascading effect in AutoTune, whereas in case of reinforcement learning, it forces them to take longer learning time. Then there is the third challenge, that is like metrics for the tuner evaluation is not sufficient right now, or there are not sufficient metrics for evaluating the tuner's recommendations. As of now, we see improvements on obvious metrics like throughput or latency, but this cannot be used on production system because say when a production database was measured for throughput, it was executing a set of workload A, and when the tuning happened, the workload can change and the same throughput cannot be compared right now. So we need sufficient metrics which can perfectly evaluate the recommendations generated from a tuner like AutoTune or CDB tune. So in a nutshell, the contributions that we try to make is as follows. We try to create a model which can check performance throttles on database. This enables the database to self-raise tuning request instead of a periodic approach. And this would break down the periodic approach of tuning. We present basic methods to apply recommendations in an effective way. And lastly, we also present some metrics that can be used for evaluating a tuner's recommendations. So the database architecture or the auto device architecture looks something like this, where we can have a tuner or a set of tuners, which can be either a Bayesian optimization style tuner or a reinforcement style tuner or a combination of them. However, on databases, VM containers, there are also a specific process running, that's the throttling detection engine as an add-on. And this is the most important component of our proposal. As you can see in the figure, a throttling detection engine is running in the database service instance. Sorry. And this is the one that is actually responsible for figuring out performance throttles. So this will enable the database service instances to raise requests on behalf of them by figuring out actually the points when the database needs a tuning and not a periodically asking the tuners every time. So how does this throttling detection works? So the throttling detection works by figuring out throttles from memory knobs, background writer knobs, and async planner estimate knobs. So let's see how the throttling detection engine works for memory knobs. So for specifically measuring throttles on memory knobs, one way is to see the utilization of shared buffers or using the known working set algorithm to figure out the pressure. Similarly, we can use something like query plans for some of the most relevant queries for measuring pressure on other memory knobs like say work mem or maintenance work mem. But problem here is that even if we are able to figure out the and say in situation when the database instances sufficiently don't have memory, then this throttling detection engine starts raising alarm or starts raising throttling detection detected throttles every 5 or 10 minutes, and that's very frequent. So we need some mechanisms to suppress this or reduce this frequency. In order to fix that, in the paper we have proposed entropy-based mechanisms which can sufficiently reduce throttling noise. Next, we want to figure out throttles for background writer knobs. The objective here is to measure disk I/O. In order to do that, the tuner needs the throttling detection engine needs to know optimal value of disk I/O utilization, and then based on that it can start monitoring disk I/O utilization. How do we come to know, or the throttling detection comes to know about the optimal value of disk I/O? So in this case, the tuner uses the past experiences of experiences to recommend what should be an optimal value for disk I/O utilization. Now, async planar estimate knob throttles. How do the throttling detection engine figures out throttles in the case of async or planar estimate knobs? In this case, basically we use a reinforcement learning approach, or in specific Markov decision process, where the objective here is to measure planner's working efficiency. So it's a simple, straightforward way where a Markov decision process tweaks the knobs and observes or learns the effect of the knob changes on planner for a given set of queries. Now, how after this throttling detection engine, the second contribution, like how do we exactly apply these recommendations? So here the recommendations are applied in two phases. So the knobs that does not require a restart, we use a SIG-hub or a config reload signal. And for the knobs that requires a restart, we accumulate the recommendations, summarize the recommendations by picking up say 99 percentile and then apply recommendations during downtimes. Now in performance evaluation, the first thing that we evaluated is, as the throttling detection engine running on as an add-on process on database instance can run scripts and figure out performance throttle, it enables the database to self-raise tuning requests instead of a periodic approach. This increases scalability of the tuner as the database now raises tuning requests only when required. So the graph in the figure shows that with throttling detection engine, the tuning requests raised for production database significantly drops. In the second experiment, we tried to measure the percentage of throttles raised by executing a read-heavy workload and a write-heavy workload. Here we say that for read-heavy workload, the throttles are mainly from background writer knobs, and for memory knobs. And similarly for read-heavy, the throttles are mainly from memory knobs and async planner knobs. Next, we evaluate throughput on production databases, and when enabled with throttling detection and when there is no throttling detection. The results here shows that the tuner's recommendations have caused an increase in throughput. And this is because the throttling detection, this is because with throttling detection, the tuner now only receives high quality samples. That is the metrics collected when the database actually needs a tuning and not during low load situations. And this effectively boosts the accuracy of machine learning models of these tuners. Lastly, we evaluated the accuracy of throttling detection. We used a trained auto-tune with standard workloads like TPCC, TPCH, or YCSB, and then we run the same workload on a database enabled with throttling detection. Now we observe the throttles and see what the tuner recommends for each throttles. If there was a throttle observed for a memory knob, and the tuner has recommended more sort of async and planner knob, this we classify as a misclassification for a throttling detection engine. As you can see, for both memory and background writer knobs, the accuracy is fine, but for async planner, it's not fine. We think that this is because auto-tune does not capture query planner related metrics, but we are confident of the planner or async throttle detection accuracy based on the reinforcement learning results that we got. So we have presented all of them in the paper, and I think you can go and visit them. So thank you. That's all from my side. You can reach out to me at my email.